What I did, I trained the neural network that I showed you on the image that I gave you. And then on my GPU, I trained a different network of a standard size of 2 million parameters on like 20 times more images with different kinds of noise in input. And this is what I got. I could start from very noisy images with the two models. With the large model, I get better performances. And by the way, if you look at it, I don't know if the video quality, the projection quality is high enough, but you can see that this actually looks nice. However, if then I will have the zoomed in images, you could see that there are some different data. You can see a lot of differences. The less noise I get, the image is always smooth in the output. This is better than the one with the small model, but we can see that the output, the more noise we have in input, the smoother the output is for some reason. And if we zoom in, we can see that with the very noisy input, we can see that all the gyri here are very, very blurred, and like this one seems to bend a bit towards the center of the head, while this one is going straight up. You can see when I flip to images how what's improving in the output of the image, the less noise that I have in input. It's not the residual amount of noise, but it's the resolution, interestingly enough. I can also use other modalities. I get the same results. And let's focus on we can focus on these structures here, which you can see that appear and disappear. But we can go to metrics, and this is the similarity index. This is the peak signal to noise ratio. We can see that the noise image has a 30 dB distance. From the true one. With the large model, I get to 40. With just the smoothing, I don't improve almost anything. And with the small model, I do slightly worse. Similar behavior are found for the similarity index metrics, even with the relative gain between the differences is better. And the more noise I have, the worse these metrics are, of course. And we can especially see that the structural similarity index that weights more the overall appearance than the mathematical differences is relatively high in the output. I also have a table of the same numbers. And that's what we can see. With a better model, we can do slightly better. We get 1 dB, and the SSIM goes from 0.909 to 0.924, but it's not really major differences. So we can get to some questions, which are, why do outputs get blurrier the higher the input noise? And why doesn't working with a much bigger model help more? And why do the images from when starting from low noise look qualitatively better to us that are not expert than the original ones? We can get now into a bit of math with the denoising theory, which I took something and inspired a lot from this. It's like a technical review paper. And it's a must read for those interested. And let's define the problem. We have a noisy image which is equal to the true image plus a perturbation. That's your general linear model that you've seen in all fields in data science. And let's assume that our noise is random and completely uncorrelated. You want a denoiser, which is something that getting in input the input image, the noisy image, and the level of noise, which we don't even need, by the way, gives us in output an image without noise. And let's say that we want to minimize the mean square error, and we want to get the estimate of the distance between the true data and the denoised data. And information theory tells us that the best mean square error will be given by this, the expectation of x given y. So what we can expect as true image given the noisy image. So, except maybe seeing math on slides, which is never the best thing, but this is apparently simple. So let's try. It's like basic calculations. So if the noise is a Gaussian noise and independent in each pixel, the probability of measuring the noisy data y given the true data x is this Gaussian function. And for each pixel, or even you can see that as a vector, they are independent anyway. If you maximize this similarity, the maximum likelihood expectation of the true value is what you have measured. So you haven't removed any noise whatsoever. And that's not really useful. We're stuck with our noisy image. So we should work with the bias theorem and do an inversion and say, what's the probability of x being the true image given a noisy measure y? We can use this inversion from the bias theorem. And it turns out that it's, again, this same term, the Gaussian, that comes from the Gaussian noise, times the probability that x is your solution, your a priori probability of x being your solution. You can do a maximum a posteriori, which you take the logarithm and so on and so on. You get the sum of squares again, minus the logarithm of the probability of x being your solution. Or, equally, the average of all the images weighted by their probability. Now, this is intractable. Integrating over image probabilities is not something that you can do. This is something we can do. I remove all the slides about reviewing the bias theorem. I suppose that in data science you're pretty familiar with that. So I just skipped over this in the previous slide, but let's ask ourselves, what on earth is the probability of an image? Let's assume that we are working with black and white images with just 256 gray levels and n times n pixels. If you take a purely combinatorial approach, that's how many combinations you get. And with a 4x4 image, which is not something, you can't even spot things in a 4x4 images, you get 10 to the 38 combinations. With 8x8, you get 10 to the 154, which is more than the atoms in the universe or the moves in chess. We know for sure that the fraction of this combination looking natural, whatever that might mean, is something extremely low. But how can we define a distribution? Let me check. Just a second, I'm just checking if... Ouch. Sorry, that's not the most recent version, that's the previous year version. Vi ho caricato il file dell'anno scorso, l'avevo migliorato per quest'anno, da qua in poi. Ve l'aggiorno in tempo reale su... Ah no, c'era qua, denoising theory comment, scusate. Ho aperto quello sbagliato. Pazienza. Ok. So let's start where we were left. Okay. So we will find that the models of images is something like that. We have a random combination of pixels. We have images with some particular frequencies, more even closer images, and only a very small subset of that is real images. Now, it turns out that the visual system is tuned to recognize some possible images. If I ask you to remember this kind of images, even if you weren't really focusing, given that I didn't even warn you, and I ask you whether this one was an image that I showed you, you know. If I ask you to look closely at these images, and I ask you whether this one was one of them, probably you don't have any clue. It turns out that this actually was an image that I showed you before, but the visual system cannot process these images. It's tuned to structures typically found in the world, for which we have been training since we were, I don't know, probably we start seeing at 3 months old or something like that. So we can work with the concept, more the practical use of the statistical model of images. What's the probability of an image? Now, this is a completely random distribution of noise. And let's start with with some kinds of images. This is a picture of the sky in a night without the moon. These are a picture of clouds. These are some test line used by optometrists, which our brain sees really well. This is a tool, some tool images, let's say, used for visual to study color perception. And because it was similar to paintings by Mondrian, this class of images is called Mondrians. This you can see, it's an ink sketch. And despite being just edges, we can process it extremely well. This is CGI, and it's a very nice representation of the world, but your brain sees, I don't know if you can see that with the quality and the background, but you can perceive that it's CGI and not a real picture, a natural picture. And indeed, there was a processing framework called Unreal, especially for that. That's a natural image. And okay, so when we want to denoise an image, what do we want to do is to remove all these random variations while preserving all the visual cues that instead make us perceive what kind of framework this is. Like these variations are not random, but it's what our brain uses to perceive that is kind of a mosaic. So let's skip over quickly over some statistical models, and let's see what comes up when you try to do that. So let's start from this image, and let's try the simplest model that we can come up with. It's where we can call it the zero-order model, and by that we mean let's take the probability of a pixel, every single pixel being of a certain intensity. We can extract an image from this distribution. So what are the assumptions of that? All pixels are independent, and the distribution of the intensity does not depend on the location. And let's say we fit the model on a night sky with stars. We generate images with this probability, and we get a really plausible distribution for this case. Let's work with a natural image. What can you guess that we will get? Indeed, if we try to apply this model where every pixel is independent, it won't work on most kind of images. If you apply that to these three kinds of images, it works only on one. Let's go to the first model. While starting from the zero, we have one pixel here, and we take a look at the correlation between pixels at all possible distances. That's just in your Gaussian model putting a covariance. It turns out that if you plot the correlation between pixels in this image, you get a very high level of correlation, especially for the closer that you are. So you might think that we are up onto something. By the way, this is what we get, the intensity of the correlation depending on the distance, and we get some correlation on the vertical. We have lots of lines. A much longer correlation on the horizontal. Makes sense, given the image. And it's interesting to notice that if we work in the Fourier spectrum, we can see that many natural images have very strong preferential directions, and it's the power of the Fourier transform, which is related to the correlation between the pixels at a fixed distance, decreases with a power law. While when you have random noise, the power of the frequencies is the same everywhere. Turns out that if you do that with 6,000 images, you get this kind of spectrum that goes 1 over f to some power between 1 and 2, with some preferential axes along the horizontal and the vertical. So it seems like we are really onto something. We try to sample new images. We start from some clouds. We generate images according to this covariance matrix, and we get something which is a bit cloud-like. If we take a picture of some hairs, we also get something. However, if we try to do that with stars, with everything else that is not cloud, we fail. We can use that to denoise images. Up to a point, you can estimate an optimal filter that's not really the most effective nowadays, but it works. We can work on more advanced concepts. We can see, like, if we take natural images and look at the edges, we can see lots of energy being concentrated along edges. While if there is noise is really everywhere. And this introduces the concept of sparsity. You have heard of that in other courses, like when you do a lasso fit. So if you know that a signal is sparse, and the sparse means that a signal is sparse if it's zero almost everywhere and non-zero in few points. However, most signals are not like that. However, it's assumed that most natural things, not only in images, but all natural occurring phenomena, can be represented as sparse after an appropriate transform. So how did it work? How did that work in history? There was the concept of Gibbs energy, and we say that the prior probability of an image is the exponential of some function of the image divided by kT, which is a physical term to imply some energy related to a temperature. but you can just take out a constant. So all of the research, starting from the 70s and going to 2017, when a neural network came, was working with that assumption that you can find some way to represent a function of the image. And they started at the beginning with, let's minimize the intensity of the image, but that might work just in microscopy or in astronomy where all the background is black. Natural images are, you don't have any reason to prefer no signal in most pixels. Then they were preferring that the norm of the gradient was reduced. This is a kind of a ridge regression on the gradient. So you say edges are not present. Then we went with total variation, which is make edges sparse, what I just shown you. Then they went to let's not work on edges, but let's work in an optimal base and let's try to invent optimal bases. So this is, again, the figure that I've shown you after we have seen all of these models. These are all images with the intensity distribution. These are the ones with the frequency spectrum that behaves like that. These are images that are sparse in some bases or in frequencies, in edges. And these are the actual natural images. So a very small part, and this model is not even perfect. Some is even going farther than that. Now, this math was working extremely well. Like that in 2009, some people asked themselves, is denoising dead? Because you could get really excellent results. And however, and they were working with increasingly complex algorithms that, however, were producing really, really minor improvements. It was a phase of diminishing return. You make an algorithm 10 times more complex, more difficult to run, and you get 0.1 dB of better signal-to-noise ratio. And it was proven that from a theoretical point of view, there was bound for improvements, but they were not there yet, even if it was really amazing what they were doing. Now, let's talk about a generic AI denoiser. This is, so what you have is a very large, whatever that might mean, data set of clean images, and you define one denoiser. I'm not even saying that it's a convolutional neural network or even a neural network. It's one denoiser, whatever that might be, and it's parametric. What it means is that it's described by some parameters, which in case it's the weights that you learn during training. You define a loss function which defines the distance between your noiseless images and the denoised images. In general, it's the mean square error if your corruption is Gaussian noise, and you minimize that. Now, do we need the 40 years of previous research? Mostly not, sadly. And this is what happened. This is the total variation. This is the peak signal-to-noise ratio on a standardized data set. And that's the total variation, so making edges sparse. It's at 27.5. In black, it's all the traditional algorithms, and that's the most recent denoising. We can see that we gained a whole dB. And this is based on transformers. This is convolutional neural network. And of course, that's specific to a specific data set, but the rankings are kind of like that. They're still very close. Now, and remember, what can we say that we brought over from the past? Locality. If you are working with convolutional neural networks, or even with patches when you're using visual transformers, you give priority to local inference, to the closest neighbors. and also that of sparsity, because neural networks in general, what they do is transforming the image in a compact representation in one latent space. And also size similarity, because if you are working with attention, it promotes recurring features over all the image. It was also discovered that that you can also use the same math to solve inverse problem, like you have a downsampled images and you want to come back to the full original resolution, and you can do that. It's really, the math just tells you that here you just want to optimize this problem. It's still an optimization. And if you take as a prior probability the prior probability given by a neural network or an AI-based system, you can solve this problem. And you can see that with neural networks, we have this is the true image, this is the downsampled and linearly interpolated ones, well, not linearly, cubically interpolated one, and you can go back almost identical, because what you're doing here, philosophically, is you have a neural network, you are fitting given this image here, you are fitting which is the most likely true image, given that you have seen all possible existing images in the universe. So what you're doing when you're denoising, you are doing a fit. Say, given my data, what's the most likely, what's my most likely input image? And you are doing a fit considering that you've seen all existing images in the universe. Which brings us to this question. By the way, the first time that I've seen this plot, I didn't truly understand it. This scheme, it's not a plot, it's a scheme. But now I think that it's really important, so I don't know if I can explain it well. So suppose that this is the, on the x-axis you have the value of 1 pixel, and on the y-axis the value of the one neighboring pixel. On the green line are the combination that makes sense in a natural image. Natural images lie only on this line of combination. Your noisy measure is here. When you do a denoising with a model that was trained to minimize the mean square error, you end up here and not on this line here. Why? Because you are, what you are doing is actually what I've told you that it's mathematically intractable, but the neural network does that. It's basically giving you the weighted average of all the images that are compatible with your measure. And the farther you are, the more images are compatible. So more images are being weighted together in a very complex, nonlinear way, but this is what they're doing. That's why they get blurrier. So you get farther, but it's not still a feasible solution. It's not a natural image. So the perceptual quality is necessarily worsened. That's a very important concept, and but let's see what they used to do during the boom of neural networks. There were some other brute force approaches of let's try and see. They were getting these blurred images and said, let's change the loss function. So a popular solution was to use the so-called perceptive loss. So what you did was you get your input, your denoiser, and you don't take the output, but you feed the output in a standard neural network that works on natural images, like this popular classifier. You extract the output as at a certain layer. Some say that the first one had were more reflecting edges, the later ones were more reflecting concepts. You do the same on your true image, and you impose that the output of the network is the same. This means that a neural network, and you say, okay, this neural network extracts all features that are relevant to natural images. In some way, this representation will look more like a natural image. It works up to a bit. The quality is perceptually better. However, where do you get? If everything goes well, if the network you've chosen is right, if you are going at the right depth, you might get maybe to the nearest point on the feasible manifold, but that's not guaranteed. Another very popular solution around 2020, 2021 or so on is a generative adversarial network. So you say, okay, let's even get a separate neural network, learn what's a good solution. So you train your denoiser in one step, and in the following step, you trained a neural network to recognize a true image from a denoised image. And you train these two networks simultaneously. In this way, the denoiser must end up giving you in output an image which is natural looking, because if it can be distinguished by another network, it will be, it's not realistic. However, what happens is that the training is extremely hard, because if one of the two networks for some reason is training much faster, then the other collapses. You don't get any way to influence which of the many compatible solutions will be found, and often, sometimes it happened that the output of this network collapsed. So a network was producing only the same image in output because this image was feasible, and so it gets stuck there. So it wasn't very successful. Where do we are nowadays? We have diffusion models. We have said that we have, let's say we are here, we have all of these images which in some way are near enough. Suppose that we get this image here, this very noisy image here. This is the true. We get the mean square error denoising, and we get this image which is a bit blurry. But what we can do is, okay, let's take all the images that are somehow compatible. You get a diffusion model, which we will not get in how it works, and it's a stochastic procedure, so it will give in output one random sample of all the compatible images, and you can see the head is inclined in a slightly different way. The eyes maybe are more open or more closed. One is smiling, one the mouth is closed, and so on. And we can see also how this works in other cases, and with many different options, like with degradation, with partial occlusion, with I don't remember the name of this kind of corruption. It's a partial masking. You get like one random pixel out of 10. This is not noise. This is just keeping one pixel out of 10. And you can see that in this case, like the hairs are blurry, while in all these samples, they are very defined, but they are in a different position each time. And the same for like the mouth here, which was invisible, or also here. So we can get, just to define what's the difference between discriminative versus generative AI. In discriminative AI, you find the probability of a target Y given the observation X, while in generative AI, you have the probability of the observation X given a target Y. As an example, I give you the picture of one number, and I ask you what's the probability that this image is the number 1. Instead, the other case, I give you the number 1, and I ask you what's the probability that this picture is of the number 1, and if I then sample, I can take this image or not. That's the inversion given Bayes' theorem, and to get one plausible image, you need to sample the model. Okay, some questions up to now? Now let's see some some quick mixed tricks about that. What happens if you don't have the ground truth? Now suppose that we have two paired set of images corrupted by noise with the only properties that this noise has zero mean. I've used the letter D as a generic kind of noise. It doesn't even have to be Gaussian. And if you minimize the mean square error, the network will be able to learn exclusively the true distribution, because you cannot learn noise, because noise is a random process. So that's really useful in many cases. There's another technique which is called the noise to void. This has some minor applications. This is specific for every single image. So suppose that you don't have any ground truth at all, you don't have matched samples, but maybe you have a very large image. You divide it into patches, you take out one pixel, and you try to predict it from all the other ones. So you trained a network to predict the central pixel from random patches of that one image. You're working with one image. Sorry about that. So you get this noisy patch. You remove this pixel. You ask it to predict it. You train a network to do that. And we get a network that works well enough. That's a comparison between the UNet, the ground truth, and this noise to void. However, what happens is that this works exclusively if your noise doesn't have any pattern, because if you have a pattern of noise, the neural network in this case will learn it, because that's present, that's a regularity, and the neural network will look for that regularity. Okay, so that's everything about the noising and what's behind that.